In the past few lessons, we've dealt with calculations that look like these, where we take a function value and multiply it by a width to calculate the area of a rectangle, and then add a bunch of those calculations together. And in a function like this, where my function's always positive, I get an area. In a function like this, some of the rectangles are facing downward, and these calculations would work out negative, and we could actually think about that as a net area, or if the function itself was for velocity, we could think of it as a displacement rather than a total distance traveled. But one of the ideas we've had is that we want to go from a calculation like this that approximates area with a finite sum and actually find the exact area. And our idea so far has been to use more and more rectangles, or chop the x-axis up into more and more little subintervals to let n go to infinity. Well, the examples we've done by hand, we've used fairly small values for n. To get a really good approximation, we might have to use a fairly large n. And our real goal is to take a limit as n approaches infinity. So we need a more handy way of writing down very long sums and doing calculations based on them. Fortunately for us, there's a way to write down summations using what is called sigma notation. So, when I say summation, I mean just adding a bunch of things together. Sigma notation gets its name from the Greek letter sigma, which in the Greek alphabet takes the place of our letter S. And it gives me a nice, easy way of writing down long sums. So I need to tell you what every part of this means. The Greek sigma means summation. So anytime in a mathematical setting I see that symbol, I know I'm going to be adding a bunch of stuff together. K is called the index. My index has a starting value and an ending or stopping value. So when I see this, I know this is a sum from k equals 1 to k equals n, and in here I've written a sub k, and this is taking place of a kth term formula. The idea is that k starts at 1 and then increments. K is 1 for the first term, and then it's 2, 3, 4, all the way until I get to the final value n. And then this summation would say, well, I'd get a first term plus a second term plus a third term all the way until the nth term. And our end goal is to apply it to a set of ideas like this. But for now, let's do a concrete example rather than just this kind of general understanding of it. So let's evaluate the sum from k equals 1 to 5 of k squared plus 1. Okay, so my index starts at 1. So I plug in a 1 for k, and 1 squared plus 1 is 2. All right, so that's what happens when k is 1. Plus, now k is 2, and I'll get out a 5. And I just keep doing that all the way until I get to 5, my stopping value. So I need to plug in k equals 3, k equals 4, and k equals 5. So this sigma notation sum was just expressing these values all added together, which if I add all this up, I will get 60. So this sum is equal to 60. So this is my sum in sigma notation. This is my sum expressed without sigma notation, and here's what it is equal to. Let's do one more together. So this sum, again, fairly easy, but there's one big difference. Look at the index. Instead of starting at 1, the index starts at 0, just telling me that the first value of k I will plug in is going to be 0, and the last one I plug in is going to be 3. All right, when k is equal to 0, I get 2. When k is equal to 1, 1 cubed is 1 plus 2 is 3. When k is equal to 2, I get out 10. And finally, when k is equal to 3, I get out 29. Add all those numbers together and I get 44. K equals 0 and k equals 1 are pretty common places for an index to start, but they can actually start at any value you want them to. So we might have an index that starts at 5. We might have an index that starts at -100. Regardless, we can evaluate sums.